Hello everyone. Last week I was invited as a guest lecturer to my university, the Royal Institute of Technology, as part of their ethical hacking course. I talked about the basics of binary exploitation. The talk was recorded, so I'm putting it up here for you all to enjoy. I also just want to remind you all that on Saturday at 3 p.m. UTC, we're doing the first test run of the pwnable race. So 4 players will be competing against each other to be the first one to solve a pwnable challenge while we have some live commentary on that. So check it out. I think it's going to be super fun. Enjoy the lecture.
Thank you. Hello everyone. So thank you for the nice introduction. My name is Kalle, or Carl, and I'm going to talk a little bit about binary exploitation, low-level exploitation, what that is and how it works. This is going to be a fairly technical lecture, and I will be assuming some knowledge about some things. So if at any point there's something you don't understand, feel free to. I really want you to ask questions. So just raise your hand, and we'll take the question immediately. And then there will also be time for questions at the end. So first of all, can you see this text? Yeah, it looks okay. It's a little bit small, but hopefully you will see it. So as Pontus said, I studied here at the KTH, studied engineering physics and a master's in computer science, and currently work as the head of security at KRY, or Livy as we're called internationally. I play these hacking competitions, capture the flags, which I think are kind of similar to the lab exercises you have in the course, but in a competitive setting. And if you want to get in touch with me at a later point, you can, for example, use one of these contact methods. So if you have any questions about this topic in particular, or security in general, I will happily answer your questions. So what we're going to talk about today. So first I'm going to give a little bit of background, like explain what we're talking about, and some prerequisite knowledge that you need to know. And I want to remind you a couple of computer science concepts that are important. Then we're going to look at exploitations based around the stack, and then move on a little bit about what kind of protections there are and how you can bypass those protections. And then towards the end, I'm going to talk a little bit about heap-based exploitation, and finish off with some further materials that you can look into if you're interested in learning more about this topic, which I really hope you will. I'm going to assume that you have basic programming skills, interest for security. I guess that's why most of you are here, and have a bit of understanding of low-level programming languages such as C, and some basic understanding of how a computer and operating system works and how the programs interact with the operating system. That's kind of the background knowledge I've based this around. We're going to talk about binary exploitation. So first of all, what do I mean with an exploit? What is the thing that we're studying here? So basically, an exploit is an unintended behavior in your program. You might remember from your more theoretical computer science courses that we can model our program as a state machine, and throughout our execution, this program will transition between different states in this state machine, and typically has one starting state, and then you have a couple of other states that you can reach. And then there are also invalid states, which the program should never be in. And an exploit is basically a way to get to an invalid state from the starting state in this state machine. And particularly, it's how to reach one of the dangerous invalid states of a program. There are a lot of ways a program can reach an invalid state, and that's what we typically call a bug. And typically, it causes some inconvenience, or the program crashes, or it deletes all your save files, or whatever. But we are interested in the particular states that are dangerous, and this is of course very context dependent, what you can consider dangerous. But we are going to just look at the kind of like general case where we are able to completely take over control of the program and make it do whatever we want. That's typically dangerous. This is in contrast then to a vulnerability. So a vulnerability in a program is a transition from a valid state to an invalid state. So this is what enables us to create an exploit. So this is the bug in the system that enables this transition from the valid to the invalid state, which we then can exploit by creating an exploit. So that's just a little bit about what we're talking about, and kind of like some kind of theoretical model of this, though this talk will be very practical and not that theoretical. So also want to remind you of, this might sound very obvious, but computers, they operate on collections of bits, and we typically group these bits in groupings. Typically our base group is 8 bits, which we call a byte, and then you have 16, 32, or 64 bits, which we typically operate on. These are kind of like our base blocks that our typical computer operates with. And what's very important to remember when you work with this kind of exploit is that these bits in the computer, they have no inherent meaning. There is nothing that tells the computer, or the computer doesn't really care about what these bits represent when they are stored there. So the same 4 bytes, which you can see in this black box. So the numbers 65, 66, 67, 68, that's 4 groupings of 8 bits, which we can interpret as 4 numbers. We can also interpret these as an ASCII encoded string, which is the string capital A, B, C, D. We could also interpret this as machine code, which in the x86 architecture corresponds to the instructions to increment the ECX, EDX, EBX, and ESP registers. That's also a valid interpretation of these 4 bytes. And we can also interpret this as a large number of 32-bit numbers, which you could write like this in a hexadecimal notation. So all of these are equally valid interpretations of the same data. And it's all depending on the context where this data is used, which of these interpretations matters. So that means that data which is originally stored in one context with one purpose can at a later stage be reinterpreted as something else in another context. And this is very important to remember. Also want to remind you that when we store numbers in our computers, we typically store them in something called a little endian format, which means that if we have a 32-bit integer, we will store the lowest 8 bits, the lowest byte, will be stored first in memory. So this number, 44, 43, 42, 41 in hexadecimal, that will in memory be stored with the lowest byte first. Okay, so in my example here I had 44, 33, 22, 11. So the 11 byte will be stored first in memory. So kind of reverse order in what you would expect, possibly, depending on your background. But this is really important. So you have this little endian format. And this is then in contrast to what's called big endian format, which is just the opposite, where you would store the most significant byte first in memory. So these are some basic pieces of knowledge that will be important to keep in mind throughout all of this. So, as I said, we are looking at binary exploitation or low-level exploitation, and that means we will be working with low-level code or machine-level code. So, in some kind of hierarchy of abstractions, we have at the very bottom, we have the physics, the electricity and stuff that goes through our circuits, and we create circuits out of this, which we abstract this, and then in these circuits, we run this machine code. And very closely associated to machine code is assembly language. Typically, assembly language is like a human-readable representation of the machine code. And you can pretty much create a one-to-one mapping between assembler instruction and machine code instructions. So from this previous slide, the assembly instruction increment ECX, which we would write as inc ECX in assembly, that would then be translated in x86 machine code to the number 65. So that's typically a one-to-one relationship, so it's very easy to go back and forth between assembler and machine code, unlike higher level abstraction. So we typically have then a hierarchy of programming languages, where we have low-level programming languages like C or Rust, which are compiled down to machine code and are executed directly on the processor. Then we have like a mid-level languages like Java and C#, which are compiled into a intermediate language, which is then interpreted by a virtual machine before it's executed. And then you can have higher level languages, which are interpreted languages, which are typically just not compiled and just interpreted as you go. So we will be moving here in the machine code world, and occasionally involve some C code and assembler. So the topics, or like the concepts I will be explaining, they are typically generally applicable for all kinds of computers and architectures in a lot of cases. But to be able to give concrete examples of things, we will today limit ourselves to x86 architecture, which is one of the mainstream architectures that you encounter in your day-to-day work. So it's like x86 and ARM are probably the two most popular architectures. So there will be some things that are specific to x86 architecture, but the concepts are generally applicable. So when we have a program that we execute, typically in our operating system, that program is assigned a chunk of virtual memory, and the program does then organize this chunk of memory into different regions, which are used for different purposes. So in the lower addresses, we keep the actual program code and some global variables and related data. And then a further bit up, we have the heap, which is the region of memory that has no inherent structure. So the structure of the heap is kind of defined by the program. This is where you place objects of various types that can have a long lifespan or short. And then, and when the heap needs more space, it grows to higher addresses. And then we also have the stack, which is a much more structured piece of memory, and it operates like a stack, like data structure stack. So you can push and pop elements from the stack. And to be able to use the memory efficiently, we put the stack in a high address. So the bottom of the stack is at the highest possible address. So when you push something to the stack, that will be saved in a lower address. So this is not very intuitive, but it's extremely important to remember. So the stack grows from a high address to a low address, and it shrinks from a low address to a high address. I'm going to repeat that throughout this because it's important. So also in your processor, you typically have a couple of registers. So a register is like a global variable that's very fast to operate on. And you typically have then a couple of general purpose registers, which are used for whatever you want. And in the x86 architecture, they are called A, B, C, and D. And then they have different prefixes and suffixes depending on how big a register you want. So the EAX register is the 32-bit version of the general purpose register A. And then so on for B, C, and D. Then we have a couple of special purpose registers, which are used for a specific thing. And one of the most important is the instruction pointer, IP, which points to the location in memory where the next instruction that we're about to execute resides. So this controls what the program is doing. You have the base pointer, which I will get back to later after I explain some other things. You have the stack pointer, SP, which points to the top of the stack. So this means, again, that when we push something to the stack, ESP is decremented. And when we pop something from the stack, ESP is incremented. Yes. And then when you're running code, you typically have functions or coroutines or whatever you want to call them. And the way the program knows how to go back and forth between different parts of the code is controlled by something you call a calling convention. So the calling convention is kind of the protocol for jumping into a function, passing arguments into the function, and getting back to the place where we were. So the typical standard calling convention in x86 is done by pushing the address. So we have a call instruction. We want to call this instruction, which is at address deadbeef. So the way we do this is that we take the address of the instruction that comes after this call instruction, which is then the instruction that we want to execute after we've finished executing this function. We take the address of that instruction, we push it to the stack, and then we jump to the location of this function. So we then execute this function, and then at the end of the function, there will be a return instruction. And what that does is it pops the top element from the stack and assigns it to the instruction pointer. So we jump back to the place we were before we called the function. So that's how we call a function and how we know where to return to afterwards. And to pass arguments to a function, we also push them to the stack in the following way. So let's say we have some C code that looks like this. We're calling the function f with arguments a and b. We then push these arguments to the stack in the reverse order that they are written. So we first push the b argument to the stack, and then we push the a argument to the stack, and then we call the f function. And this is then where the base pointer comes in. So throughout the execution of a function, we have then a bunch of local variables that are local to this function, and we have a couple of arguments that we pushed to the stack before executing this function. So if we want to refer to these local variables, for example, we could refer to them relative to the stack pointer. So in this case, the local variable 3 would be the stack pointer plus 8, because since we are in a 32-bit architecture, like this, the base size, the element, the size of like the base element is 32 bits. So each of these blocks is a 32-bit value. But addresses are counted in bytes. So every value you push to the stack will increment or decrement the stack by 4. The problem is that throughout the execution of our function, we might push and pop things on the stack. So it gets very confusing how we would refer to these local variables, because the offset from the stack pointer to the local variable will change throughout the execution of the function, and that's extremely annoying and sometimes not even possible to keep track of. So what we do is we introduce something called the base pointer. So throughout the execution of a function, the base pointer will always point at the same place. And that means that all the arguments and all the local variables can always be referred to relative to the base pointer. And that offset will always be the same throughout the execution of the function. So if we want to refer to the first argument that was passed to this function, we look at the base pointer plus 8. And that will always be true throughout the execution of this function. And if we want to address the local variable 1, we can take the base pointer minus 4, and that will always be true throughout the execution of the function. Yes, question?
If I'm not mistaken, compilers that perform optimizations might not use the stack for some parameters, but instead might use registers. And in that case, is there an easy way to identify this behavior?
Yes, so this is called a calling convention, because it's a convention, and the compiler can choose to break this convention. And also in other architectures, they use a different convention. So in 64-bit x86 architecture, you typically use registers more for passing arguments. So this is one calling convention, and this is one way of doing it, and this is a very common way of doing it, but there are other calling conventions. But many of these concepts or ideas still apply. Yes. So the base pointer is basically, it's set to the top of the stack when the function starts, and then the previous base pointer is restored when the function finishes execution. So we can now move into and actually look at the first very basic kind of exploit. It's a simple stack-based buffer overflow. So let's say we have this C code, this vuln function. So this function defines one local variable, which is an int, so that will take up 4 bytes on the stack. We also define a buffer, which is 16 bytes large. So in total, this function will allocate, or it will take up 20 bytes on the stack, apart from these bookkeeping values, like the saved instruction pointer and so on. And then we call this function, fgets, to get some input from the user and save it in this buffer. But this function has no size limits or any restriction of how much data you can insert. So if we look at the stack, so this is kind of like an representation of the stack. So first we have this 16 bytes buffer, then we have this local variable, this integer, which is 4 bytes, and then we have this the saved base pointer, so the base pointer of the previous frame. We don't really care about that right now. And then on the stack we have the return address that we're going to return to when we're done executing this function. So if I would just input then like 4 A's, 4 B's, 4 C's, 4 D, and so on, I would get this crash. I get the seg fault, and it said that it crashed at this address. So what has happened here is that when this function reads data into the stack, it starts writing at this address where buffer is, and it then just goes on. So first it writes these 16 bytes to this buffer, then it overwrites the integer variable with 4 bytes, then we overwrite the saved base pointer with 4 bytes, and then we overwrite the saved instruction pointer with 4 bytes. So at the end of this function, when the ret instruction is called, we will pop this value from the stack, which is hex 47, 47, 47, 47, and we'll try to jump to that location. And most likely, there isn't any valid code at that location, so the program will crash. So, I mean, that's something, but not very interesting. So what we can do then is introduce something called a shellcode. So as I explained previously, there might be a lot of different goals when you're trying to exploit it, but a very general thing is just to launch a shell from which you can do whatever you want. And this is a piece of assembly code that launches a shell, and therefore it's called shellcode. And it's typically called shellcode even if it doesn't launch a shell. So any kind of like small snippet of code which does like the thing you want to do is called shellcode. So you don't need to understand like all the exact details of this piece of code, but basically what it does, it launches /bin/sh. And if you run this through an assembler, you will get the following bytes as an output. So this is the machine code representation of this shellcode. So if we go back in time a couple of years, where we had really no protections. So let's pretend we're back in like 96. At that time, the memory layout of the program would be completely predictable. So we would know the address of the stack when the program was executing. So this means that we know the address of this buffer variable in memory. So what we now can do, so let's say that this address is this BF/FF/FD/B4 address. So what we can do now is we first write this shellcode as input, takes up a couple of bytes, and we then pad out with a couple of null bytes at the end. You see after the 0BCD 80, and then we have a null byte. And then we are at the location where we want to put the return address. So there we write this BFFFFDB4 address, which means that at the end of the execution of this function, when we call the ret instruction, we will pop this address from the stack and assign it to the instruction pointer. So we will then point the instruction pointer to this buffer on the stack and start executing code on the stack. And this is valid code. So it will run this code, launch a shell, and we are in control of the program and can do whatever we want. So this is like the first very basic example of like a low-level exploit, a basic stack buffer overflow. So here we could place the we had enough space because we had these 16 bytes plus these 4 bytes and then 4 bytes we didn't really care about if they got destroyed. So we have enough space to place the shellcode there in the beginning of the buffer we are overflowing. But it doesn't really matter. We can of course place the shellcode afterwards in the memory. So first we just fill up some dummy values and we then put in the address of the next 4 bytes, and then we put the shellcode there. And that also gives the same result. Or in any other location that you know the address of. For example, if you have some global variable, which is your username, and you can set your username to whatever, then you can set your username to the shellcode. Yes? Yes, absolutely. So now you see that the address which I written there ends with a B4, and then the address we actually put in ends with D0, which is 24 bytes more, if I'm counting correctly. So yes, we have to, of course, adjust the address. But if we don't know exactly in memory where this is, we might know roughly where this is. Maybe this program has executed a lot of stuff, so we have pushed and popped stuff from the stack, so we don't know exactly where we are. We have a problem because this shellcode that we have, for it to work, it requires us to start executing exactly at the first byte. If we start executing at the second byte, we'd skip the first instruction and the code will not work as intended. So we can give us a bit of wiggle room by using something called a nop sled. So a nop instruction is an instruction that does nothing. And one such instruction in x86 is hex 90, which is a nop instruction. So what we can do is we pad out our shellcode. We prefix it with just a bunch of NOP instructions. And that means that as long as we just hit any of these NOP instructions, let's say we land somewhere in the middle of this sequence of hex 90, that will execute a NOP instruction which does nothing, and then go on to the next one which does nothing, and so on. Just execute NOP, 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 NOP until we reach the code that starts doing something interesting. So that means that we have more space we don't need the same precision when jumping to the right address, and we'd get the same effect. This is what you could do like 25 years ago. But now we have started introducing protection, or since long ago we have introduced protections. So one such protection is something called ASLR, which stands for Address Space Layout Randomization. And this means that whenever you launch a program, the starting address of the stack is randomized. Roughly on a typical, I think in Linux, I think it's about like 12 bits of randomness, which is enough to cause a problem. So we really don't know where the stack is located at all. So the NOP sled trick doesn't really help us, because we can't write like several hundred thousands of bytes of NOPs. That's not the typical scenario. What can we do here? So ASLR has kind of two parts to it. One part is to randomize the stack, which it always can do, no matter how the program is created. But it can also randomize the location of the code in memory. But that requires the program to be compiled in a way that supports this. So if you don't have this, the stack is random, but the location of the code that the program has is known, will always be in the same place. And we can then find a piece of code that's already in memory which does something that we want to do. So such a small piece of code is called a gadget. So for example, if we have a gadget that has the instruction jump ESP, which is like jump, so change the instruction pointer to the location of the stack pointer, we could utilize that to jump to where the stack is, even though we don't really know where that is. So if we can find such an instruction somewhere in the code of the program that we are exploiting, and this program is not compiled with support for being randomized, we will know where in the memory this snippet of code exists, this gadget. So when we introduce our shellcode into the buffer, see, we don't know where in the memory that is. We just know that on the stack, at the top of the stack, we have our shellcode. But if we instead then jump to this address 40001004A, which we know where it is, that will execute that instruction, which will jump to the stack pointer, which will then jump into our shellcode. So that way we have defeated this stack randomization protection, for example. And this will then execute our shellcode. Another protection, which was actually introduced earlier, but it's easier to explain them in this order, is called NX or DEP. So DEP stands for Data Execution Prevention, I think, or protection. And what it does is that it gives every region of memory permission bits. So in the same way you typically have permission bits on file system on Linux, you typically have like read, write, execute for your files. This creates the same kind of permission bits for pages in memory. And specifically, it marks the stack as readable and writable, but not executable. And it marks the program code as readable and executable, but not writable. And this is then a problem, because even if we put code on the stack and we manage to jump to that code, the program will crash because it's not allowed to execute instructions in this region of memory. So how can we defeat this? So I mentioned these gadgets previously, and that was like a simple gadget to jump into our shellcode on the stack. So it was just like a small stager. But if you remember this, so this return instruction, what it does is it pops an instruction from the stack, pops a value from the stack and jumps to that location. So if we look at the code and we find different pieces of code which ends with a return instruction, we can chain these together. So for example, if we have these two pieces of code somewhere in memory, so one piece of code is pop EAX and then return, another piece of code is pop EBX, pop ECX and then return. And what we can do then is, if we want to control the contents of the EAX, EBX and ECX registers, we can set up the stack in the following way, as you see in the third block. So first we have some dummy values, and then we overwrite the return instruction. Sorry, not the return instruction, the saved instruction pointer, which we will return to. We overwrite this with the address of the first gadget. We then put the value which we want to assign to the EAX register. We then put the address of the second gadget, and then the value that we want to assign to the EBX register, and then the value we want to assign to the ECX register. And we execute this. This means that first, at the end of this vulnerable function, we will jump into the first gadget. So we will have popped that address. So now the top of the stack is at this dead beef value. We will then pop this into the EAX register, call the return instruction, which will pop another address and jump to that address. We will then pop another value, the Cafe Babe value, put it in the EBX register, pop another value, the feed food value, and put it in the ECX register. So in this way, we are chaining together existing pieces of code which are already in memory and jumping from gadget to gadget and manipulating the state of the program. And by doing this in a smart way, you can kind of like create this basically is like your custom programming languages, where every one of these gadgets is like one of your basic instruction, your basic building blocks. And you can then chain them together and hopefully do whatever you're trying to do. So this is called return-oriented programming, because like the core mechanism here is that we are executing these return instructions that pops an instruction, an address from the stack and jumps to that instruction. So this way, we don't have to introduce any code ourselves, but instead we introduce values that the existing code will operate on, and we will then control what code is being executed. So that's a very powerful technique, which then circumvents this whole DEP protection, because we're only executing code that is allowed to be executed. Yes, question?
But that code that is already allowed to be executed,
yes,
is not malicious. We do not control what code it is.
Exactly. As a whole, it's typically not malicious. But we're taking pieces throughout the code. So we're just taking a few instructions here, a few instructions there. So I mean, somewhere in your code, you probably are doing some kind of system call, maybe just opening a file, for example. And that is one instruction to do a system call. And somewhere else in your code, you have something that pops a value from the stack and puts it in the register. But that register also happens to be the one which control which system call you're using. So you first execute this first gadget to set up the value of this register, and then you jump to this other instruction to make a system call, which now actually does not open a file, instead it executes a program. So you're chaining together these different pieces of the code in an unintended way. It's basically, this is the machine code equivalent of me going into the original source code and copy pasting individual lines of code into my own program. So if you write a completely benign program, I can copy paste individual lines and rearrange them in such a way that the program becomes malicious. So I'm just gonna check. Yeah. So let's do this and then have a break. So another protection that you have is something called Stack Guard or Stack Canary. It has a couple of different names, but the idea is the same. So what happens is that when you're compiling your program, the compiler inserts a couple of extra instructions. So let's say we have written the function to the left. This is our vulnerable function. When we compile this, the compiler will insert a couple of instructions at the beginning and the end of the function. So what it will do is, when the program initially starts, it will generate a random value, a random secret value, which is stored in a place where the program can retrieve it. And what happens then is, when you execute this function after the compiler has modified it, the first thing that happens in your function is that the program will take this secret value, push it onto the stack, and then execute the function as normally. And then before calling the ret instruction, because we know that's the dangerous part. Like if the ret instruction receives, like if we control the value that we're returning to, that's what creates problems. So before executing the ret instruction, we will look at the stack again and check that this value is still the same secret value. Because if it's not, that means that something has overwritten values on the stack and tried to overflow the stack frame. And that's not a good thing. So the program will instead just crash in a controlled manner, and the exploit will fail. So, for example, if we have our stack set up as in the second line there, you have this secret value, which is, for example, FE48 at the 1A C9, and that's placed on the stack after the, or before, depending on which direction you're counting from. So next to the saved base pointer, and then you have all the local variables. So let's say we have this overflow in the buffer on the stack. We overflow it, and we overwrite this secret value, which we don't know what it is. We overwrite it with just a couple of Fs. And then at the end of the execution of this function, the program will see that this FFFF is not the same as this secret value, and therefore we will crash, and you will get something like this, stack smashing detected, program terminated. And the way you can like get around this kind of protection is, I mean, this is kind of self-evident, but if you know this value, we can just overwrite it with the same value and then continue writing whatever we want. So the whole mechanism relies on the fact that this value is unknown to the attacker. So if you have another vulnerability in the program where you, for example, can leak parts of the memory, you can then combine this to leak out this stack cookie and overwrite, when you're doing this overflow, overwrite it with itself. So then when this comparison is made, the value will still be equal to the secret value. The program will not crash, and we will have control of the instruction pointer. Yes, a question?
Is it random when each execution?
Yes, so it's random. So every time you start the program, it's randomized. And this also means that if you have a program which is kind of some kind of server that forks, it will be the same in each fork. So this is another way of circumventing this protection. So let's say you have some kind of server, and for each incoming connection, it forks off a child process and handles your connection and your data. What you can then do is you start with the first byte. So you just overflow into 1 byte into this stack cookie, and you try all the 256 different combinations. So you will get the crash, and you connect again, you overflow with another value, you get a crash. And for one of these 256 values, you will not get a crash. So then you know you guessed the correct value for the first byte of this stack cookie. And then you just redo this for the next 3 bytes. So that will take somewhere between 0 and 1,000, or 4 and 1,000 attempts, which is much better than 2 to the power of 32 guesses, which is probably not feasible. So yeah, if you can make multiple guesses into a forking process, you can also circumvent these protections. Yes, so let's have a break and continue after the break. We have talked a little bit about these stack-based exploits. So before we move on to the heap-based exploit stuff, I would like to go through a couple of other topics. So one thing that we didn't cover, which is a very interesting, a little bit odd kind of exploit, is the format string vulnerability. So if you've ever programmed C or a C-like language, you used the Printf function, which has this interesting function signature that you have one argument, which is your format string, and then you have a variable number of additional arguments, which are the values that you want to populate your format string with. So a typical call to this function would look like something like the first one. You insert a format string, saying like first we want to output name, colon, and then we have a placeholder here for a string that we want to output, and then a comma, space, age, colon, space, and then another placeholder for a number that we want to output. And then we provide this string and this number as 2 additional arguments. So this would be a perfectly fine way to use this function. The problem arises when the attacker can control the first argument, the format string. So in the second example, maybe you have some name variable and you just directly pass it to printf. So if you would just input a string there, we would just output the string. So that would be fine. The problem is that we can then put these placeholder values, these format string placeholders into this variable and cause problems. So first of all, this function takes a variable number of arguments. So how does the printf function know how many arguments you have passed to it? And the answer is it doesn't. But it assumes that the number of arguments you have passed is the same as the number of placeholders in the format string. So as we've seen on this stack layout image, yeah, exactly. So I'll just use this image again. So as we've seen before, the first argument will be the base pointer plus 8, the second will be base pointer plus 12, and so on. So when the printf internal algorithm is parsing this format string, it keeps track of how many placeholders it has seen so far. And when it encounters a placeholder in the format string, it will just look at the base pointer plus 4 times the number of format placeholders we have found so far. So in this first example, if I would just put a %x, so x is the format for output a number as a hexadecimal in hexadecimal notation. The algorithm will then look at the base pointer plus 8, but we didn't actually pass any argument. So we didn't push anything on the stack there. So there will be something else on the stack there relating to the function that is calling printf. And so on. And if we put another %x, we will read the next value on the stack and output it onto the screen. And we can continue. Just fill this up with %x, %x, %x. We will just start reading out the contents of the stack and output it to the user. Okay, so what? I mean, maybe in some situation there could be some secret value, and it says an information leak. That's bad. So, you know, for example, we could leak out this stack cookie, for example. So let's say we continue all the way down to the bottom of the previous frame, and we just dump out this stack cookie, and now we have it, so we can do this stack cookie overwrite thing that we talked about earlier. So that's good. So that is what I would call a direct read. We are directly reading an element from the stack. You can also use the %s format, which is used for reading strings. And the way this works is that the actual characters of the strings are not placed on the stack, but a pointer to those characters. So the %s will treat this element on the stack as a pointer to memory, and it will start reading that part of memory and just printing everything out until it reaches a null byte, which is the end of string, and then it will stop. So if we can control a value on the stack, we could put an address on the stack previously, and then we put this %s in. We can then use that pointer and read memory from somewhere else in the memory. So that's also interesting. So that's what I would call an indirect read. We are using a pointer and we are reading the destination of that pointer. So if you can control the value of this pointer, you can read whatever memory you want from the program. There's actually, so printf, like the name says, is typically used for like outputting things. But you can actually also write memory with printf. So all of the different these format placeholders in printf are used for formatting something for output, except %n. And %n, what it does is it treats the next argument as a pointer to a number, and then it writes to that location the number of characters you have outputted so far. So since we control the number of characters we have outputted, we control the value that's written to this destination. So if we can put a pointer on the stack to some location that we want to write to, and then we put the %n in the format string, we will write to that location and overwrite a memory. So, for example, if we knew where the stack is, we could use this to overwrite the saved return instruction and use that to exploit the program. And the good thing there is that since we are writing directly to a specific address, the stack cookie doesn't even matter, because we're basically just jumping over it and writing directly to where we want, if we know where the stack is. But we can, if we have this format string vulnerability, we can know where the stack is, because the base pointers that are saved on the stack, they are different locations on the stack. So we can leak out one of these saved base pointers. We know where the stack is, and then we can use the stack to write to one of these return addresses and overwrite it. So that's another way you can use this to write memory and exploit things. Another thing which is really cool, which I actually learned quite recently, and I failed to solve a problem due to not knowing this, is that you can also kind of copy values from one part of the stack to another part of the stack. So the way, if you're using this %n thing, a very nice way to control the number of characters you have printed so far, and thus the value you are writing to memory, is to, so the naive way would just be to start the string with a number of A's, the number which is the same number as the value you want to write. But a more convenient way is to use the padding function. So when you're using printf, for example, if we want to print our hex values so that they always take up 8 characters, we want to pad them out with 0, so they always take up 8 characters, no matter how big or large they are. We can write %08x. That means pad with zeros to the length of 8 and format in hexadecimal. So that means that we always print 8 characters. So if that we can then extend this to whatever value we want. So say that we want to write the value 137, we can just write 137x. That means that we will first out, we will take something, treat it as a hexadecimal value, print out 137 characters, which means that this n counter will be at 137. So that's kind of like the direct way to set this value that you're writing to the memory. But if you use this 0 asterisk thing, you're instead saying, like, look at the next argument and treat that as the width of this value that we're printing out. So basically the normal usage of this function would be, say, you have %0 asterisk x, and then the two following arguments would be maybe 10, and then the value we want to print out. Then it will first take this 10 and say that, okay, I will print it so that it takes up 10 characters, and then I will print this value that we want. So this means that we can use this to look at one value in the stack and print that many characters, which means that this n counter will be set to that value, so that we then write the same value somewhere else in memory when we use the %n modifier. Yeah, that's a bit, I think you have to kind of like sit down and work through this to fully get it, but the point is that you can copy values from one place of the stack to another place in the stack. You can also use this $sign thing to, if you have something that's interesting that's further down the stack and you don't want to pad out with like %x, %x, %x to get to the right place, you can just directly say $4, then you will just skip to the fourth argument and print out that value. So with all of these different capabilities, if you control this format string in a printf function, you have like all of the different primitives that you would want when you're exploiting these kinds of programs. It's a very powerful exploitation technique, and also quite fun because it's a bit like odd, like abusing this function in this way. Another interesting thing is, for example, if you only have a small overflow on the stack, maybe you can't reach all the way to the instruction pointer and overwrite it, or you have some other kinds of limitations, or you don't know where to jump to, you can use this the saved base pointer and overwrite it. So as I said previously, this the base pointer is used to reference arguments and local variables in a function. And when a function finishes execution, it will then pop a value from the stack to set it to the base pointer of the previous function that we are returning to. So they are kind of stored in a chain. And that means that if we change the value of the base pointer, we are effectively changing the value of all local variables and all arguments in that function. So if we can, somewhere in memory, let's say that the previous function has some interesting value that we want to change. If we then can kind of set up a piece of memory somewhere where we know the address to contain all the important parts that are required for the program not to crash, but with this local variable change, and we manage then to change the base pointer to point to this part of memory instead, we can kind of like replace the whole stack frame and the values of all these local variables and parameters. So that would enable us to control the values of local variables in a function. And that is, of course, very context dependent if you can do anything interesting with that or not. But you know, it could be something like a variable that says, it's a flag that says if you have admin access or not. And then you overwrite this base pointer so that you change all the values of the local variables and you change the value of this flag from 0 to 1 and you have admin access, for example. That would be one way that this could be used. The problem is, of course, that you have to make sure that all the different values that are accessed have values in such a way that the program doesn't crash, because then the exploit will fail. So it can be, it's quite tricky to set it up, but it can be a very powerful technique when you can't directly overwrite the instruction pointer. It's also possible to, since we have this little endian representation of addresses and values, that means that if we just overwrite the first byte of a value that's stored on the stack, we're overwriting the least significant part of the value. And that means that that's effectively the same thing as adding or subtracting a small number from the address. So, for example, if we know that further down the stack or further up or down the stack, we have values that we control, but we don't know in absolute terms where this is, we can just overwrite the first byte of the base pointer to just effectively shift the stack up or down a slight amount. And that's another way then to create, to control all the local variables and the parameters of the stack. So that's another interesting technique. Yes, question.
So, how do we use this? Like, do you find someone's source code and you look into it and you look where they have programmed it wrong?
Yeah, so it's a very good, because the question is about like how do you even find these vulnerabilities? So there are different methods, and in general, it's always, of course, easier to have the source code. So typically a lot of interesting things that you want to attack are open source. So you can look for vulnerabilities by directly reading the source. If it's a closed source program, you can use tools to disassemble and decompile the program. So you take the program and you take it from machine code and you translate it into assembler, and then you can read the assembler, and you can, if you have nice tools, you can even revert it to like C code, so it gets more readable. So that's kind of like the what's called like static analysis. You read the code, you understand it, you find bugs in it. There are also like general like code analysis tools, which are the same that a developer would use to help find bugs. Also something called fuzzing. So basically, you run the program through an automated system which gives the program a bunch of different inputs until it tries to make the program crash or makes it end up in an invalid state. And then you investigate how could this happen, what kind of input made the program crash, and you kind of work your way backwards, and hopefully you can then create an exploit out of that. So that's another technique. Or just like using the program, trying things manually, so like manual testing. So like every input field you input all kinds of crazy stuff, like a normal testing engineer would do in like a QA process. So there's like a bunch of different ways of finding these vulnerabilities, and they have pros and cons, and they're typically used in combination. But for small programs, you can typically just disassemble the program and read it and understand it. But typically most real world targets are typically larger things, like an operating system or a browser or things like that, typically huge code bases. And there you pretty much need tools for automating parts of the process. Yes, so two other types of protection I just want to briefly mention, which are kind of new. One is called control flow integrity, which is basically a way so the compiler, basically when you compile the code, it inserts a bunch of extra instructions and protections. So it basically creates a list of places that you're allowed to jump to. And that means that typically you're not allowed to jump into the middle of a function, which this return-oriented programming technique is based upon. So if you have this kind of protection and you're trying to use ROP, you're trying to jump into the middle of the function, the program will say no, that's not allowed, and crash in a controlled manner, so your exploit will fail. The way you would bypass this is that in some cases it's not possible to determine beforehand if it is allowed to jump into a certain place or not. Typically, that's the case when you have programs that generate code during execution. So you have something like a just-in-time compiler. So for example, a JavaScript engine typically optimizes parts of the JavaScript code. If it recognizes that this part of the JavaScript code is used a lot, it will translate it into machine code and like compile it and create a piece of machine code to execute that function. And then you don't know beforehand what that's going to look like, so you can't really create like a white or black list if you're allowed to jump there or not. So that's a place where this protection doesn't work, and you can then exploit that. Another very new protection is something called PAC. So things called pointer authentication codes. So this requires special support in the hardware. So this exists currently, I think, on 64-bit ARM architecture. So they have added new instructions into the architecture for cryptographically verifying the integrity of pointers in memory. So if you would overwrite a value then on the stack to overwrite the return address, when the program is about to return to this, it will check if this is a valid address created by the program as part of the normal execution, and if it's not, it will crash in a controlled manner. So the way this works is that in 64-bit architecture, your basic block is 64 bits, but your memory space is typically not 64 bits because that's a huge amount of memory. So typically you only use, I think, 48 bits for addressing. So you have about a couple of bits left over in your pointers that will pretty much never be used for anything interesting. So those leftover bits will be used to store the authentication code for this pointer. So when a call instruction is made, for example, it will not just push the return address to the stack, it will calculate with the secret key an authentication code for this return address, then push that to the stack, and then verify this authentication code when you pop it. So there's cryptographically signing all the pointers in memory. So as I said, this is available in 64-bit ARM. So for example, the iPhones have this, the newer ones. And I think there have been some bypasses on this now, but I'm not really up to date on the details on that, how you would bypass those things. And I think it's fairly context dependent. You use other methods specific to the iOS operating system to make your exploitation in a different way. So this is a very interesting technique. It's a very powerful protection, or it takes I mean, a lot of effort has been put into this because you've actually created new features in the hardware and new instructions in the architecture just to protect against these kinds of exploits, which I think is very interesting. So I'm going to finish up by talking a little bit about the heap-based exploitation. So this is not at all going to be as thorough as the stack-based parts, because this is also typically very context dependent. So I'm just going to talk a little bit about the general ideas. So when you launch your program, so your computer has some physical memory, and then your operating system uses this to create virtual memory, which it hands out to programs. So when you launch your program is assigned some amount of virtual memory, and this is divided into pages, which is fairly large chunks of memory, typically something like 4 or 8 kilobytes of memory. And the program can ask the operating system to give it more pages to work with, and it can return them to the operating system if it feels that it doesn't need them anymore. And then within your program. So from the operating system, you can only request full pages of memory. But in your program, you typically use a lot of objects which are very small. So what you have is you have a memory allocator. And this depends on what programming language you're using or what version of the C library and so on. But you have a memory allocator. So when you call a function like malloc, so allocate memory, that has an internal data structure, an internal algorithm for dividing these pages up into smaller chunks and keep track of which of these chunks are available and which of these have I already handed out, and so on. You will have this heap where you have these pages of memory, and then the memory allocator will slice this up into smaller part as needed and hand it out to the program. And when the program calls the free, it will mark them as available for handing out again. So there are kind of like two levels you can exploit the heap on, two conceptual levels. One part is to attack the actual memory allocator by manipulating these internal data structures that keep track of what memory is available and what memory is not. So typically you have a couple of tables, and these chunks of memory are linked together in a linked list data structure that keeps track of how big these chunks are and where the next available chunk is located and so on. So if you have a couple of objects in memory like this, and let's say the first one is allocated to the memory and it represents some object in your code, like a book in a library or something. And you have an overflow on the heap. So let's say that we can overflow the title of the book to write further into the heap. We can then write into the next chunk of memory, which is, say, it's marked as available in this memory allocator, and we can then overwrite these like metadata fields about this chunk of memory and corrupt this linked list of available memory chunks. And this can then lead to interesting situations where the memory allocator thinks that part of the heap is actually on the stack. So you're able to use the heap object. When you call malloc, you actually get a pointer to the stack, and you can write things to one of these saved instruction pointers to take over control. Or we might get two pointers pointing to the same chunk of memory, or other kinds of mix-ups. And this can then, depending on the context, lead to like further corruption of the memory and then taking control of the system. So that's kind of like attacking the actual memory allocator. The other part is kind of attacking like the application layer. So let's say that you have some kind of program with a bunch of different objects. So for example, in C++, for example, it's very common you have inheritance and polymorphism, where you have these V tables, which is tables of function pointers. So it tells, if you have a C++ class and you have an inherited class and you are overriding or overloading a function, you will have this V table that keeps track of which function we're actually going to call. Are we going to call the one in the base class or in the inherited class? So that means that in these objects on the heap, we will have pointers to functions that we're going to call. So that means that if we can have this situation, let's say we have allocated this first data chunk, and we overflow into the next one, and we manage to overwrite the V table of that object, we can then overwrite this function pointer. So when we're trying to call this function, we're actually calling some completely different function, and we take control of the execution. Another common thing is something called a use after free. So when you call a free on a pointer, you tell the memory allocator that I don't need this piece of memory anymore, you are free to hand it out somewhere else. But it doesn't actually prevent you from using that pointer again. So if there's a bug in the code where you call free, but for some reason you continue using that pointer, what can then happen is that the same piece of memory is allocated somewhere else. So you have two pointers pointing to the same piece of memory, but one pointer is of one type and the other pointer is of another type. So two different parts of the code will view the same piece of data as representing two completely different things. So let's say again we have maybe this like library thing in the book with a title, which is a string that maybe you can edit, but in another part of the code that's actually part of this vtable for another object. So you change the title of a book to an address in memory, and then this other part of the code will then use this as a function pointer to call some piece of code that you control, and you have taken control of the memory. So this is called something called a type confusion, where different parts of the code thinks that the same data represents different things. Yeah, so that's pretty much what I had for the actual content. So I know that I have gone through a lot of content, and to actually like get to know these things, you pretty much have to like sit down and try this out yourself. And there are a lot of good resources to try these things out. So as I said in the beginning, I am part of this Capture the Flag team. So we play in these hacking competitions, CTFs, and there are these competitions pretty much every weekend. So you can go to this website, ctftime.org, where they have a calendar of all the events and kind of like an unofficial world ranking scoreboard as well. There are also some of these competitions, some of them are more difficult, or some of them are more beginner friendly, and some of them, for example, the Google Capture the Flag, they have a specific, what they call like the beginner's quest. So they have a specific set of problems which are suitable for newcomers. And there's also something called War Games, which is pretty much the same thing as a Capture the Flag, but it's running all the time. So it's a website with challenges that you can solve. Yeah, pretty much like these lab exercises, I think, that you're doing in the course. So one of them is called Pico CTF, which is really good. It's a CTF that ran, I think it was during the fall, but they have left it up. So all the challenges are still there and you can try it out. And it's really good. It's originally aimed for like high school students. So it starts at a very friendly level and then it ramps up quickly. Really good, really well-made competition. If you want to specifically look at these, so these competitions, they do not only include these binary exploitation challenges, they include challenges of a lot of different categories, like web and cryptography and these binary exploitation, or pwnables as they are called in this context. So if you want to specifically try out these binary exploitation challenges, there is this website, pwnable.kr, a Korean website, with they have basically handpicked good challenges from different contests and stuff throughout the years, and create kind of like a really good mix of challenges, which also starts out in a fairly beginner-friendly level and then gets really tricky. There are a couple of good YouTube channels, including my own shameless self-plug, and some of the tools I would recommend to check out. So for writing these exploits, I typically, and a lot of people, use Python with a library called pwntools, which has a lot of good like helper functions to interact with programs and create these exploits and so on. For debugging a lot of these functions, at least on the Linux side, you have GDB, and there's an add-on called pwndebug, which is really good. Gives you a lot of different helper functions and ways to visualize memory and so on, which helps you a lot. And then for doing these analysis of the programs, like you asked about, there are a couple of tools. Radare is like the open source alternative. There is a GUI version for it as well called Cutter. Then there's a program called IDA, which is like the commercial professional tool. They have a free version, which you can try out. It's a bit expensive, so maybe not your first go-to. There's also a program called Binary Ninja, which is a more recent addition to the scene. And it's really cool program, and it doesn't cost several months of salaries. So that's maybe more if you start getting into this and think that yeah, I really want to learn more about this and I want to upgrade my tooling, I would definitely look into that. It's a really cool, and they have a really nice scripting interface for automating things as well. So this whole presentation I've given today is kind of could basically be more or less like a half semester course. And if you want to find such a course, there's this RPI-SEX Modern Binary Exploitation. So this is like a student organization at one of the universities in the US. They have created this course for binary exploitation and put all the course contents on GitHub. So they have slides and lab exercises and stuff like that. If you specifically want to look more into these heap-based exploitation, there's this GitHub repository by one of the best CTF teams called How to Heap, which contains a lot of good resources. And as I said, if you want to get in contact with me later on, my contact details are being in the slides. I think we can get the slides out somehow, right? Or
yeah, so we're recording it all. So
yeah.
In that way, it will be available for you.
Okay.
And if you submit your slides to us, we can also post the slides if you just want the slides.
Yep. That's good. Yeah. So with that, that's all from me. Thank you very much.